Today's video will demonstrate how to implement the graph using an array of edges. Hello, I'm James Helfrich. The array of sets, otherwise known as the adjacency list, is one of the four implementation options for the graph. This video will demonstrate how to do that. There are four implementation options for the graph. The first one is interconnected nodes, which is sort of like a linked list. The second is a set of edges, where every element in the set is a source-sink pair. The third is an array of sets, which we'll talk about today. And the fourth is a grid, where the horizontal axis is the source, the vertical axis is the sink, and if there is a true in that source sink location, then there's an edge there. We're going to talk about the array of sets today. The UML class diagram for the array of sets consists of a graph class, and the graph class has the usual public methods, a constructor, an assignment operator, empty, size, and clear. It also has an add, where I'm going to add a new edge, remove an existing edge, is edge to determine if an edge exists between a source and a sink, find edges, find a set of all edges from a given source, and find path, which will return a list of vertices from a source to a sink. Now notice how add, remove, is edge, find edges, and find path all refer to a vertex. Therefore, there is a vertex by reference. We also have an adjacency list, which is a set of n edges. And so we have a set where T is a collection of vertices, and there's going to be n of these because we're going to have an array of sets, and every T is going to be a vertex. And there's going to be between 0 and n vertices. 0 if there's no out degree for the given vertex, and n if a given vertex has an edge to every other vertex in the graph. To demonstrate how this works, we're going to have a graph of 5 vertices, and they'll be by default vertex 0, 1, 2, 3, and 4. The implementation is going to be an array of 4 sets. Initially, these sets are empty. The first set corresponds to the source 0, the second corresponds to the source 1, and so on. Now I want to add an edge between vertex 0 and vertex 1. So between 0 and 1, there'll be an edge, which means for the source 0 and the sink 1, we're going to have one element in that set. Now I want to add a vertex between 3 and 0. So source is 3 and sink is 0. Therefore, the 3 source will have a 0 sink. Now I want to add a vertex between 3 and 2. So between 3 and 2, there'll be an edge. And therefore, I'm going to add 2 to 3's set. Now I'm going to add a vertex between 3 and 4, between 3 and 4, and therefore I'm going to add 4 to 3's set. Now I'm going to add a vertex from 2 to 0. So from source 2, sink 0, and therefore set 2 is going to have a 0 sink. Now I'm going to remove a vertex between 3 and 4. So I'm going to look at source 3, and that set consists of 0, 2, and 4, and I'm going to remove that edge, and I'm going to remove that sink vertex. And now I'm going to add a vertex between 0 and 4. Now, currently, there's a vertex between 0 and 1, and now there's going to be a vertex between 0 and 4. Therefore, I'm going to add 4 to 0's set. Let's take a look at the pseudocode for the 4 most important methods. The first is edge. I want to know if there's an edge between a source and a sink. So the way I'm going to do this is I'm going to have my adjacency list of source, and that's going to be my set of sinks. And I'm going to find if that sink is in there. If it is in there, then I have an edge. If it's not, then I will not. Now notice this is O sub log m, where m is the out degree of the vertex. And the reason for this is because find for a set is O sub n. In this case, n is the out degree. The next is to find all the edges corresponding to a given source. In essence, I'm just going to return that source's set. And that's O sub 1 if I return a reference to the set, or O sub n if I'm going to make a copy of that set. If I like to insert an edge between a source and a sink, then I have to insert the sink into the source's adjacency list. Now, insert for a set is O sub n. Well, there's not n vertices. There are m vertices, where m is the current out degree of the edge. And the final is remove. I like to remove an edge between a source and a sink. And here I'm going to call the sets remove. And this also is O sub n, where n is the out degree of the edge. Okay, let's take a look at this example. Pause the video and see if you can draw the graph corresponding to this array of sets. Okay, let's begin. Now, first of all, we have 4 edges, alpha, beta, gamma, and delta. Alpha, beta, gamma, and delta. Now, I'm going to first look for alpha to alpha, which means I'm going to point to myself. Then I'm going to look for alpha to delta, so I'm going to point to delta. Then I'm looking for beta to alpha, so beta to alpha. Then I'm going to look for gamma to alpha. So gamma to alpha, and then gamma to beta, and then finally gamma to delta. So gamma to delta. And notice how there's no edge leading from delta to anything. Here's another exercise. Again, pause the video and see if you can draw the array of sets corresponding to this graph. Okay, so I have 8 vertices. So initially they're empty. And I want to first find all the edges corresponding to node 0. And I'm going to go for 0 to 1, 0 to 2, and then 0 to 4. Then I want to find all the edges corresponding to vertex 1. And so 1, 2, 3, and that's it. Then I'm going to look at vertex 2, and 2 goes only to 4. Then I'm going to look at 3, and 3 only goes to 6. Then look at 4, and 4 goes to 0, then 4 goes to 5, then 4 goes to 7. Let's look at 5 here. 5 goes to 4, 5 goes to 6, and 5 goes to 7. Then I'll look at 6, and 6 only goes to 4. Finally, I'm going to look at 7, and 7 only goes to 2. There's my array of sets. You can learn more about the array of sets implementation of the graph in the graph chapter of the C++ data structures textbook.